Almut has invited me to give 2 lectures. There'll be 2 2-hour lectures, one starting now and the other 2 o'clock in the afternoon for those who still wish to hear and see me, what I have to say. So I've divided into 2 blocks. One is about power system operation, which is about the fundamental principles according to which the power system works. And the other will be in the afternoon about power system modeling. I'm sure all of you will know some of it, most of it, but I don't think any one of you will have seen, come across concepts which I'm putting across. So if some parts of the lecture are well known to you, so just bear with me, and I'm sure there'll be something exciting right around the corner. The most important thing I'd like to emphasize is that I'll be, well, this is for mathematicians, so I don't try to compete with mathematicians on equations because I would lose. So I'm trying in my lectures to concentrate on the physics and engineering which is behind the equations. And I think this is absolutely fundamental. Because I've been working with mathematicians for over 10 years or so, and of course you put equations in front of mathematician, that's perfect. But quite often people take wrong assumptions because you have to always simplify models to a certain extent in order so you can do some mathematical analysis on them. And the key thing is those simplifications. Do they make some physical sense or they don't make physical sense? And in order to make this judgment, what is allowed, what is not allowed, you need to understand it. So that's why my 2 lectures will concentrate on understanding, rather than just here is another equation. Of course, at any time, feel free to stop me and ask questions. And also that content, which I'm putting over here on the board. I mean, there's a number of textbooks on power systems, and there are again equations and etc. So you can find them. This is not the deal. But I think some of the concepts which I try to explain, especially I'll be talking today about reactive power, which is a very dodgy concept, and even power engineers don't understand them. So I've had many discussions. I mean, Chris was actually the first version of that course, which I gave about 10 years ago or so. Maybe something like that. We had this big EPSRC funded SuperGen program, so I gave this boot camp and I gave those lectures. So the power engineers in the room, and they didn't understand. If you ask power engineering what is reactive power, they'll say, well, it's Q, but what's behind it they don't understand. So this is some of things which I'll try to concentrate on. So this morning lecture I'll be talking about main power system characteristics, why power system looks the way it does, about the future power system, how it is changing. Then we'll talk about maintaining power balance, that means power flow equations. I'll be talking about those AC, DC models and explain what's behind them. And I'll be using illustration using historic blackouts. Blackouts are my favorites, one of my favorite subjects, because blackouts are like a lightning, In a dark room there's lightning and you can suddenly see the landscape. It is something like that. It is like lightning usually because there's some short circuits on the way. So all the fundamental characteristics come up alive and you can see what's happening. So I'll be using towards the end a lot of slides regarding blackouts. First thing is, I'm not sure if people are aware what actually, when you're talking about electricity, what does your bill go to, and this is the most recent breakdown of electricity bill, domestic bill from August 2018. So many people think, well, electricity bill is energy. It's not only energy. If you look energy, at the moment is 33%. And what's interesting, and as I look at the previous version of those slides, when I had it was 2013, 5 years ago, it was just over 50%. So the percentage of energy in your electricity bill has dropped quite dramatically from 58 to 33. You know why? Well, this is my supposition. I have no proof, but I think I know the reason why. Any ideas? 2013, how does the generation profile has changed over the last 5 years in this country? A lot of wind. Dramatic increase in wind and in solar. And of course, when you check, which means that the percentage of the wholesale cost of energy has dropped, But if you look over here across, environmental and social obligation costs have increased quite dramatically. So some of that increase is probably due to wind and solar pushing downwards pressure on prices, and you have to pay for them anyway, so you pay through all kind of taxes and levies and things like that. Well, direct comparison between the 2013 and 18 is different because I noticed that different classifications, so it's not one-to-one. But it's worth remembering. So 1/3 goes energy, 25% is grids network costs. There was no breakdown in this number about between transmission and distribution, so I took the number from 2013. So 20% is distribution and 4% is transmission, which is very characteristic. And again, when you, from the point of view of power systems engineers, when you talk about modeling, all the models I'll be talking about are about transmission, which is only 4% of the cost, because that has fundamental characteristics of the system. You can point out to them. But majority of actually network costs are in distribution. So from the purely cost perspective, distribution is much more important than transmission for a very simple reason. Of course, there are more distribution wires than there are transmission wires. Transmission are those big lines going across the country, while distribution is everywhere, because it brings power to individual houses. Operating costs, it's 17%. I think here is, that rubric was not in 2013, so maybe some of those operating costs were from wholesale costs, I'm not sure. VAT, interesting thing is supplier pre-tax margin. Look how tiny it is, at least if you believe Ofgem, but you remember there was a cap on energy prices, so there was all this uproar about suppliers ripping off the customers. But if you look at the tax margin, it's tiny. It's just few percent. So I don't know who do you believe, of course, but this is worth remembering those numbers.
Yeah, just want to say again what those operating costs.
I don't know. I couldn't find out. I think there'll be cost of operating the grid probably. That's why I put a question mark, because I wasn't sure what it is. So that's why I'm saying it's difficult to compare the numbers 2013 and 9 and now, because they've changed the classifications for some reasons. I put those diagrams quite recently. I didn't have time to check what's behind them, those numbers.
Yeah, another interesting comparison, which of course we have absolutely no way of doing, is the supplier pre-tax margin and supplier internal costs. Yeah. So a lot of what they do is just pass costs through.
No, but yeah. And well, I don't want to go into this long discussion. There's David Newberry here and his team, and they deal with those kind of the economic issues. Do they really rip us off or not? The actually interesting economists tell me, when I remember all the changes to the suppliers, because that thing has been going on for a number of years, and every changes they brought in, Ofgem brought in to sort out supply side, were actually for worse. They made situation far worse. This is law of unintended consequences. So people take decisions based on what they think it should, like, without asking economists what the consequences are. And some of those changes were clear. People were saying, David Newberry Group and others, don't do it. It's wrong. And it was wrong, but they still did it because it made political sense, because it's easy to give interviews and telling, oh, we are defending customers. But I don't want to go into that. I'm an engineer. Oh, by the way, sorry, I didn't introduce myself. So my name is Janusz. I should have started from that, because there are many people I do know, but many people which I don't know. So my name is Janusz Bialek. I'm currently with Skoltech, which is a new international Russian university based in Moscow. I'm part-time and flexible contract with them. That's why I can spend a lot of time here. And also from next month, I'm joining Newcastle University, also on a part-time basis. So I'll have 2 hats on my head. And my background is power systems. So I'm an engineer, but I've been working with economists and mathematicians for 15 years or so now. Chris, who is eminent person in power system field, I'm responsible, for example, to bringing Chris to the area of power systems. I attracted him against the Bank of Scotland or Royal Bank of Scotland.
Interviews on the same day.
In the interviews on the same day. I always like to say that it's my fault that there was a 2008 financial crisis, because it was just before the crisis, and had Chris gone to them, to the risk assessment, whatever they're doing, he would have prevented it. So it's my fault. Anyway, so how the power system looks like. So these are kind of typical diagrams, which I'm sure you have seen many times before, so I'll just go quickly through them. So if you look at the power system in the 20th century, power systems has started at the end of 19th century in the United States, and in here, Westinghouse, I think, and Edison were the first who constructed power systems. And they actually, if you look at those systems which they constructed at the end of the 19th century, throughout the 20th century, it all looks the same, just things get bigger and better. So the main characteristic was, so you had power stations, and power would flow from the power stations to individual houses through transmission lines and distribution lines. So there's unidirectional flow of power. The demand was highly predicted and passive. Basically, people would just consume energy, and it was, you could predict it with high probability, kind of very little error, less than 1% normally. There was a limited number of those big power stations, so those power stations were getting bigger and bigger in time, and they were controllable by the system operator. Very limited energy storage. It was just pumped hydro. In this country, we have just two pumped hydro stations, and we don't have hydro as such too much. Dispatch generation had to follow the demand. So if you look at the typical demand, daily demand curves over different seasons, so those curves were highly predictable. And basically, generator was scheduled to follow a predicted shape of demand, winter, summer over here. It's important to understand that this infrastructure has been put in place long time ago. I'm talking about the wires. Of course, power stations are changing. So we have still to live with old legacy infrastructure in terms of lines, transformers, and some of them are 50, 60, 70 years old. It's pretty old stuff, and it will not be changed because it would cost too much. So all the new solutions which we are all working on have to live with this old legacy infrastructure. So if you look at the planning, how the system was planned and controlled, so planning means infrastructure, generation, transmission, distribution was planned to serve the peak, load, and reserve. So that was the fundamental planning. So basically, if you look again at those curves, planning target was a certain percentage above the predicted maximum demand because you need some reserve, and while these were the actual operating curves. So if you look the difference between the planning target and, like, let's say in the summer, there's a huge difference. That means that a lot of equipment is underutilized. So there are some numbers which I took from number of presentations. So it's about 50% generation utilization factor. Transmission is only 30% utilization. So think about it. And for distribution, I don't have numbers, it's even lower. It's probably 20% or so. So think about it. No other industry would have survived with such a low utilization rate. It's no way any proper manufacturing industry would survive with such a low utilization rate. So it's very expensive. In terms of control, centralized, hierarchical, so basically the system operators, so those system operators have those big screens and they see what's happening. They're gods. They're telling everyone what to do. They have full control on the power system. And it's hierarchical. It means there will be usually national control centers, and then below them there will be some distribution control centers. But basically the principle is they tell everyone what to do. Deterministic, of course, because everything was highly predictable, and preventive based on N-1 reliability criteria, which I'll talk about a lot, which means that the system has to be secure not only under what is assumed to be normal operation, but also when one single element fails, so-called credible contingency. Because it has to be safe as well, because anything may happen at any time, lightning may strike, whatever, we still have to survive. I put it not in Russia, because when I moved to Russia, I realized that actually Russia has never had, it's not running things to N-1 criterion, because it's impossible. Their system is so big, so stretched, they just couldn't provide enough. It would cost too much for grid to run to N-1. So they have a lot of fast control scheme, security control schemes, emergency controls. If something happens, then they immediately activate it. So remember, N-1 is considered in the West as a sacrosanct, but it's not. You may do the same things using clever control, and Russians have been doing it since forever because they had to. And this is, I think, the way we are going, generally speaking, to to get rid of this very low utilization rates, you can do things by control, but system operators hate it. Because, of course, control may fail, may be poorly designed, and then there will be failure. While if you have a lot of fat, a lot of security margin, you will survive. It's far safer, but it's far more expensive. So as I said, system is very conservative, traditional system, a system expensive to build and operate. But everyone is happy because electricity is considered as a fundamental good. I mean, the modern society cannot survive without electricity. We must have electricity all the time. And if you look at your domestic costs, it's actually relatively cheap. So people put up with it. So how the things are changing? So 21st century, this is one of those famous diagrams about smart grids, I think from NREL or one of them, one of the American bodies, which means we have a lot of good things around the place. So we have solar panels, of course, we have wind turbines over here, everything connected by communication, solar panels on roofs, storage, and etc., and etc. But remember, we are going in that direction, of course, but everything behind it, there's still the legacy infrastructure, all those transmission distribution, which we have to live with. But things are changing. So, of course, power now is bidirectional. If customers produce energy, PV, panels, wind in distribution networks, then the power can change direction, and that causes some technical problems, because the system has not been designed to live with it. Stochastic generation and demand, of course, on the last week workshop was all about it, and previous track was also all about it. The generation is no longer deterministic, it's stochastic, the same with demand. How do we deal with it? And by the way, I keep telling that system operators absolutely hate it. No matter what they tell you, they hate wind, they hate solar. They had to be dragged, kicking and screaming towards accepting it. When you talk to system operators 20 years ago, 15 years ago, when all those revolutions started, they would tell you, wind, okay, we can accept up to maybe 20% at the most on the system. If it goes above it, everything will collapse, because we can't do it, because it's stochastic, and etc., and etc. Now we have very high penetration of wind, and we still live. And they still hate it, but they had to do it because there's no other way. So, and that's thing. So basically, they hate stochasticity, but they have to be dragged to accept it. Of course, so before there were just few big power stations, now there's a large number of non-controllable stochastic power sources. So it's not only renewables, it's everything. Energy storage, it's not there yet, but it's already started to make its mark. Storage is getting more and more affordable. And how to control the whole thing? Well, fortunately, at the same time as all those changes, there are growth in ICT infrastructure. So you have a lot of sensors on the network, internet, wide area measurement systems. I was talking about this research track about those phasor measurement units, which provide a lot of information about a transmission network, what's happening in real time. So all this growth in communication and control infrastructure allows us to change the paradigm of power system planning and control. So how it's changing. So this is what everyone is saying, what will happen in this century. So we'll move control from this preventive N-1 design to corrective just in time. So rather than having a lot of fat, to use it in the actions which will react to the events. From deterministic to stochastic, from centralized to distributed. Storage changes dispatch. It's a complete game changer. At the moment dispatch, you assume the generation must be equal to demand. If you have storage, that time linkages. So that means your dispatch intervals have to be linked. You cannot just dispatch for a given time. Everything can be linked, and there's a lot of activities in this area, of course, how to optimize it. No longer demand-driven generation, because we have controllable load, so we have both sides of the equation. Not only generation of demand, we can change, perhaps. So there was a lot of talk about it. You remember the first workshop, Sean Main was talking a lot about it, how we can use controllable loads for control. So the results will be reduced security margins, cheaper operations. So we will have reduced the cost. But the main driver is not really reduction in costs. The main driver is the growth of renewables, is all the changes which are behind the power system. Because if we left the old paradigm with n-1 reliability, huge security margin, so if you add on top of that stochastic generation like renewables, that means the security margin would be just enormous. And the generation utilization rate would drop from 50% to, I don't know, 30%, 20%. So that would be absolutely unacceptable. So in terms of planning, so all those changes in control mean there is reduced need for infrastructure, generation, transmission, distribution, because you utilize the system better. So that means there will be improved utilization rates, deferred investment, basically lower cost, but we must maintain reliability. Remember, one of the first arguments when talking to system operators, for example, I'm talking to them about this frequency control and management, which I'm working on with Stephen Law. They say, yeah, but you can see the eyes, they don't believe it. Because this is to do with this replacing preventive control to corrective. Theoretically it works, but it's from the system operator point of view, having a lot of fat is far better because they know it will work. While your control may fail, may be badly designed, God knows what will happen. So they do it only if they have to. But they will not do it just like that, just to reduce the cost. Because their main responsibility is to provide security of supply. This is number one. This is what they worry about it all the time. In terms of economics, I will not talk much about economics, so just one slide. So traditional, this is PJM slide. This is the supply curve. It means marginal cost of generation as the function of a quantity. So typically, all the markets around the world are based that depending on the demand, market clearing price will increase as the demand increases, just goes to the right, and the price goes up. And it is based on the principle that price is set by the marginal generator. So for example, this one, it means all the generators which are below it in the marginal supply curve will get rents, which is the difference between the market price and their costs. And they need those rents to pay for their fixed costs. Because for the marginal generator, the price is equal to the marginal generation price. It means cost of increasing generation. Everyone has to pay their fixed costs, so this is the profit which goes towards it. What will happen in the future when we have zero marginal cost generation? It means that curve becomes fat. That means that people will not get enough rents to cover their fixed costs. And when you talk about renewable generation, majority of the cost is fixed cost because wind and solar cost nothing. So we have to think about new models, and economists are telling me there are a lot of models, but I'm not sure about it. So this is how the future. So now I'll talk about the main characteristic of the still existing power systems, which will not change. So whatever are the solutions, we'll have to live with the system as it is. So this is the map of the British power system. So my apologies for the people coming from abroad. But more or less they all look the same. Where the only characteristic thing about Britain is that we are an island. It means that DC connections to Europe is not part of the embedded in the bigger picture like in Europe, for example. Of course, the most fundamental law in power system is that generation must be equal to demand plus losses. And that generation equal demand, of course, must also include storage. Storage may generate or demand power, whatever it is. So this is the fundamental equation, which is obvious. And also, second thing, which is obvious, that power flows in the network flow according to the laws of physics. It means Ohm's law and Kirchhoff's current and voltage law. This is, you would be surprised how many people forget about it. There was a famous paper in Nature, I think, some time ago when they designed the network, the power systems, well, analyzed powers in network. No, it wasn't Nature, but it was quite high-ranking journal. It was about 10 years ago. They analyzed the American power network, but they treated it as a transportation network didn't implement the Kirchhoff's voltage law, which tells you how the power flows. And they came up to the conclusion that American network is very vulnerable and will collapse very soon, until people pointed out to them that actually this is not how the things work. So you'll be amazed by that. And we'll be talking about those laws in this afternoon. So generally speaking, flows cannot be directly routed. You cannot tell power how to flow. Mr. Ohm and Mr. Kirchhoff tell electrons where to go. By the way, electrons don't flow. It's a very complicated physics argument, but let's not go into that. Energy flows. So a flow and a given line, so if we take any given line in the power system, the flow on that line or that line, whatever, depends on the generation and demand pattern in the whole network. In order to determine how much power flows in one particular line, you need to know everything about the network. Everything is connected together. All the laws connect, physics connect all the network together. The next fundamental characteristic, there are no valves. If people compare again to distribution, to the transportation networks like motorways or water pipes, motorways and water pipes have natural thing which basically there's no more water or cars can go on the network until it's physical capability. There are no valves, but in power networks there are no valves. If there is too much power flowing in the network, according to the laws of physics, lines will overheat and they will fail. So we have to do something about it. We should.
Have you ever tried to create some kind of?
Next slide. There is congestion management requires coordinated redispatch. It means if that, let's say that line is overloaded, you have to change the generation around it and in order to redirect the flows. You cannot just tell power not to flow on that line, generally. But actually, as Beth quite rightly said, there are some attempts to this direction, but not entirely. It's not like valves, they'll help. And that's been the valve evolved just to control something what is called loop flows. Again, this is characteristic of the important characteristic of a power network. So because everything depends on everything else, and power flows according to the physical laws, not according to economics laws, so power does not flow directly from A to B, but through transmission lines. So this is, for example, the simple results of the simulation which I have done. So let's assume there's an export from a generator in France over here to some load in Italy, which is a common situation because Italy doesn't have enough generation because they voted against nuclear some long time ago. So if you look directly through the border between France and Italy, so if you take a commercial managers, they would contract a contract and say, okay, so all the power flows directly from France to Italy. But it's only 38% power flows directly through Italy. The rest flows all around the place. So for example, look, 15% flows via Belgium in the opposite direction, loops through Germany and then goes to Italy. It goes all over the place. So this is called loop flows, and of course if they are not treated if they are not treated correctly, they will overload the neighbors' networks. And this is very real problem in Europe, and one I'm particularly familiar with is the situation around Germany. So Germany, what happened was they used to have a lot of nuclear generation in southern Germany, which supplied the southern industry. But that's been replaced by wind, which is near the Baltic in the north. So what you have in Germany, you have a lot of power over here which supplies the southern part of the network and also the neighbors. And you can see the loop flows going around it via Poland, and I'm familiar with that for obvious reasons because I have some friends in the Polish system operator, through Czech Republic, but also through Netherlands, so Bert could be interested in it. Belgium, France, and it's going to the south. And look at the numbers, they are pretty big. And if those loop flows overload the network, the main reason they overload the network is that the dispatch in each of those countries is done separately. There is no coordinated dispatch in Europe. Everyone does their own dispatch and then they just coordinate export and imports. But that flow from here to there, it's not export and import, it's just due to law of physics, it flows through the neighbors. And Polish network, a couple of years ago, was so severely overloaded that at one point they wrote official letter to Germans and said, unless you do something about it, we just disconnect. Because it was overloading the network, they couldn't do it. They couldn't cope with it. So the argument is still going on, of course, let's not go into argument, But going to the bird's question is, can we do something about those loop flows? And there is the thing which is called phase shifting transformer. I'll be talking about modeling of a phase shifting transformer in the afternoon because you need a little bit of theory about it. But basically you can put those devices which try to kind of repel the flow so they not flow through it. I took last night that diagram from one of the presentation which was dealing just on this kind of western part of the loop flow. So you can see at Belgium and the Netherlands, those PSTs are all over the place because they try to push out that power flow into Germany. The same thing, they are not shown over here, but Poland has in the north and the south have those phase shifting transformers. Czechs also have them. So everything's trying to push them inside the Germany just to prevent their own networks. So there is something, but it's not like, completely. It works to some extent. And also one of the problems is that, power has to flow somewhere. So you cannot have, if you have quite closely located those phase shifting transformers, they have to be coordinated because one will push power to the left, the other push power to the right. And of course you cannot have both. So there's less lot of problems with that, but there is something about it. And as I said, in the afternoon I'll tell you more about it. And now I'll ask a few questions. So there are questions actually from my second year lectures. And I was surprised how many people don't know the answers to those very simple questions. So I'll just check with you if you know the answers. The first answer is very simple. Why power systems are interconnected? So for example, if you look at the British network, it evolved initially as regional networks, which are shown here in the blue, but then they were connected by these red lines to form one interconnected network. The same in Europe, of course, each of the individual countries had their own network, and which were then connected to form the interconnected networks, which are shown in different colors over here. So what are the reasons for interconnection? I'm sure you know some of them. Obvious reason is you basically use cheaper generation wherever it is. If you go back to Britain, cheap generation is generally in Scotland. People live in the south of the country, so you need transmission network to connect. So this is obvious thing. Any other reasons? Sorry to treat you like kids, like students.
Security.
Sorry?
Security.
What do you mean security?
Well, if you're connected to more resources, then there's more actions you can take.
Yeah, exactly. Well, another thing is for connecting, before I go to that one, is taking advantages in differences in living. This is in Europe, of course, not in Britain. If you look at the south of the Europe and north of the Europe, living patterns are different. So it's peak shaving. You can kind of equalize the pattern. But John is absolutely right because he's been working in that area for over 10 years. Sharing reserve is, in the case of this is N-1 criteria. You have huge, if you share the reserves across the network, there are huge savings. So if we have let's say three equal areas, each require 2 gigawatt reserve. So when they operate separately, you need total reserve 6 gigawatt. Well, if you do a little bit of calculation, it's obvious when you share them, total reserves, unless I got my probabilistic wrong, each loss of generation in each area is independent event. You can calculate that it's 3.46 gigawatt, which means 42% shaving. So if you look at the European network, I've checked it actually, historic sources. That was the main reason for connecting the network. Huge savings in the reserve. Look at the numbers. So actually the main reason for connecting the networks in different countries was sharing reserves and huge savings in the reserve. Why so many voltage levels? If you look at the British network, so electricity is generated in the range of about 10 kilovolts, then is carried through 132 or 275, 400 kV network. When you go closer to the customers, it's 33 kV and lowers, and we are used at 24 volts. So why do we have different voltage levels?
Power losses on the line.
Power losses on line, exactly. Transmission losses are proportional to the current squared. Power is voltage times current, so when you increase the voltage, you reduce the current squared times, so twice higher voltage would reduce your losses 4 times. But of course, increased voltage level, it means the lines cost more because it's insulation. That's why highest voltage is only for these very long transmission lines which go across the country. And if you go close to the customer, then so distribution lines, when you have shorter distances, the voltages are smaller because it's cheaper, because lines are smaller and the distances are less. Good, you've passed that exam question. Next one. This one is a difficult one. How many wires do you see? This is a picture of a typical transmission line in this country. How many circuits, how many wires do you see? And what is the meaning of each of those wires? Chris probably knows because he's been working with me a long time. So Chris, others. How many circuits do we have? Circuits, it means, you know, just connecting from A to B.
I look like that, 12.
Wrong. Any other answers? Remember, power, and I'll do the next slides about it. In transmission, distribution, generation, all the circuits are three-phase. There are three phases. So if you look at it, this is one phase, and this is the other phase. So what you have two circuits which could be independent on the same transmission tower. They could be connected, but they could be completely independent electrically. But if you look at it, how many wires do you see? For example, but this one phase, so this is one of the phase, has two wires. You know why? This is high voltage transmission line, so it's probably 400 kV. 400 kV, it means it's a high voltage, and when the air is damped, you'll have, what's the word? Discharges. It's called corona effect, right? So if it's small wire, then basically the voltage is very high across it, around that wire. So if you put two wires, that effectively you made the effective cross area of the conductor much bigger. So it means that the voltage, the electric stress will be less. So they are called bundled conductors. So this is one. So though this is the same current flowing in them, but just separated to reduce the stress and reduce the corona effect. So we have two circuits, each of them consisting of a number of wires, but it's basically the same thing. What is that thing on the top? Lightning protection. Now, of course, you have to protect it, but there's additional thing, which means, of course, the power system people realize very quickly, well, we have a piece of wire which is basically unused. Why don't we wrap around it fiber optic? So practically all transmission lines carry communication lines on top of it. So we write that fiber optic on top of those wires. But now let's go quickly through why we have those three-phase circuits. So if we, this is AC circuit, and we have, so how the power is being generated. So this is synchronous generator, which basically means how power is produced. So you have electromagnet. We'll come in the afternoon about modeling about it. So if you spin the electromagnet around according to the Faraday's law, if you have a stationary conductors on the stator, there will be sinusoidal voltage induced. I think everyone remembers something from school, how it works, Faraday's law. So you have a sine wave, this is sine voltage. So, but all those machines are three-phase, everything is three-phase. So why is it three-phase? So it is the same synchronous machine, but you have three phases on it, separate, which are 120 degrees displaced. It means if you spin the magnet around, you have three-phase voltages. You have three voltages shifted by 120 degrees. Simple functions, right? Which means if you model it, you have three parallel single-phase circuits. And the key in the three-phase circuit is you join the return wire. So current flows here, power flows here and comes back. What will happen if I connect those return wires? They connect together. Well, there will be current flowing over here, which is sum of individual phase wires. So three-phase circuits is nothing else than three single-phase circuits with common neutral. And if we collect assume the balance conditions, it means that the impedances, load impedances are the same, everything is perfectly symmetrical. So all currents flowing in the three-phase circuits will have the same magnitudes, but they'll shifted by 120 degrees with respect to each other. If you do simple math, you will see that the current is zero, return current is zero, by magic. That means what we have, if we go back once again over here, we will see that current's going from the generator to the load, but the return current is zero. You can remove all those return currents theoretically, because there is nothing flowing here. If there is nothing flowing here, we can remove it. So you can remove it, and that gives significant savings. We have hundreds of thousands of kilometers in this country of three-phase circuits, and you suddenly remove 50% of all the wires. So the savings are huge. Well, of course, there is always some imbalance currents. It means there will be some currents returning, because not everything is perfect. That the current is zero only if everything is perfect. Nothing is perfect, and nobody is perfect. It means there will be some return wire, so that the wire which you could saw on the top of the transmission tower also provides, it's not only lighting protection, it also provides a return circuit. Because you don't want the return current to flow through the earth. The simplest connection would be to earth it. But then there will be actual current flowing, which could be dangerous. I remember as a student we used to calculate the step voltage. The step voltage not in the control theory step, but actual step. Because if there is a current flowing, if you step over it, there will be potential difference between your legs. And you have to be at the safe level. And also the worms, biologists worry about, if there's a current flowing, it can damage them, and etc. and etc. So that's why you provide the return through the overhead wire. But of course, to simplify things for our analysis, when you do your math, at the transmission level you assume usually that everything is perfectly balanced. That means you replace all those three circuits by just one circuit. At distribution level it's not so easy, because distribution level, what does it mean, distribution? It means you have three-phase circuits. It will be houses connected to each of those circuits. Of course, you don't have three-phase circuits in your house, you have single circuit. So in the States, 1/3 houses will be on one phase, 1/3 will be on the other phase, and 1/3 will be on the third phase. Sorry? If you're lucky, yeah. But usually they even don't know, because again, this is legacy infrastructure. The whole thing was connected maybe 50 years ago, and no one remembers which house is connected to which circuit, because the documentation got missing. So there will be, and people go on holidays, whatever happens. So distribution lines are usually unbalanced. And then you have to do three-phase analysis, which is complicated. You use so-called symmetrical components. So you break down into positive sequence, negative sequence, and zero sequence. Everything gets messy, but you can do it. Transmission level, usually you assume everything is perfect, balanced, and so we can only analyze one circuit, and that's what we'll do in this course as well. And the last one of those silly questions is why all the circuits are AC rather than DC? And the answer is on the diagram. Well, this is simpler to analyze. Of course, people are talking about DC. The first transmission networks were DC. Actually, Edison favored DC. But then Westinghouse won on AC. And the reason is, as we said, we need many voltages, and voltages are the easiest transform from one value to the value, the other value using transformer. And transformer works on the Faraday's law. So you have a current on the primary circuit, this is secondary circuit, there is a flux linking them. And in order to transformer to work, the current has to be AC, because if it's DC, nothing is being induced. There are power electronic transformers, but they are not as efficient, and they don't work on the very high voltages. So it means in the house, of course, you may have a power electronic transformers, but you cannot imagine power electronic transformer at 400 kV level. Doesn't work. Well, the other reasons for AC also is the principle of operation of induction motor, which is the most popular motor, is the workhorse of the industry, is that it's based on the principle of the rotating magnetic flux, which induces currents and etc. And you have this rotating magnetic flux when you have a three-phase circuit. Single-phase circuits will not produce rotating magnetic flux, but this is going too much into electrical engineering, so I'll just skip it. And now, what time shall we make a break? I think it's another 5-10 minutes, and then we take a break. Okay, so I'll just start this thing. How to maintain a power balance without measuring all the generation demand. As we said, dispatch means that the system operator, God, knows what's going on and dispatches the power station to follow the demand. But what would sorry. So this happens in time scale of minutes. So they run their dispatch program every few minutes, and as they see how the demand changes, they will dispatch different types of power stations, which are shown different colors: base load and mid-merit. So the power plants follow demand. I'm talking about 20th century, of course, not 21st century. But what happens when there's instantaneous power imbalance? It means we lose a big power station. In this country, the biggest power station is Sizewell B, which is a big one. It's, I think, 1,300 megawatts. So what happens? You lose a large power station. Generation must be equal to demand at any instant of time. Power system operator does not know that something like that happened, and even if he did not know, if he did know about it, he couldn't have scheduled another generation to replace it immediately, because nothing works that quickly. So in the first instant, when you lose a large power station and there is a, let's say, 1 gigawatt deficit, it means generation is less by 1 gigawatt than demand. What will happen? How this energy is being replaced, by what? That's right. And actually, I'm giving, this is part of my typical second year lecture. So there'll be 200 students in the class. No one knows about it. People don't understand the most fundamental characteristic of the power system. Of course you do, because we are talking about frequency control all the time. Lights die on because it's covered, the missing energy is caused by the inertia of all the rotating masses. All those generators will keep rotating, and the remaining generation will keep rotating, and the missing energy will come from the kinetic energy, which means they will slow down. They are quite big ones, and that kinetic energy provides a cushion for any imbalances between generation and demand in both directions. If there is deficit of generation, frequency drops. If there is surplus, frequency goes up, of course. And that's the beauty of the AC power system, that frequency provides an indicator about power imbalance, and it will trigger control, so you can use it. And you can measure frequency anywhere. It's the same here or in Scotland. Average. It may change momentary, but on average it will be the same. And that's the most fundamental characteristic of the power system, frequency control. And that's the advantage over, for example, DC networks, because in DC networks you don't have a universal indicator which would indicate you a power balance. It's one of the problems if you move to DC. So now let's talk, just before the break, about this primary and secondary frequency control. So we can break it into what happens into several stages. So in the first instance, power deficit is coming from inertia, means kinetic energy of all the synchronous rotating masses. And if nothing else happens, if we do not connect additional generation, the frequency will keep dropping until everything basically grinds to a halt. But what will happen is that all the generators have those turbine governors, which actually James Watt came first with this idea about them. But well, of course now not mechanical, they're electronic, but principle is the same. That point moves up and down depending on the speed of rotation. So if the speed of rotation drops, that point moves and opens turbine valves. So more steam is coming through. It means more power is being generated, and the whole thing will continue until the balance will be reached. It means when the additional generation provided by all the generators on the power system will equal the power loss, let's say Sizewell B. But it's important that then it will stop, but the value of frequency will be less. In frequency, in the control theory terms, that type of the controller is called a proportional controller. And if you've done any control theory, who has done any control theory by the way? No. Well, in the typical controllers are proportional controllers, integral controllers which integrate the error, and derivative. Proportional controller will always produce a steady state error. It means the value after the control process stops, the value of the frequency will be less than 50 Hertz. So what will happen then? Well, sorry, this is in the second. So this is called primary frequency control. It means this automatic, autonomous control reaction to dropping frequency. And it's important that all the turbine governors have this frequency control, primary frequency. They must have it by law. Well, initially the James Watt invented them not because of the frequency control, because by he realized that if he doesn't have them, basically the whole thing will blow up. So there was a fundamental thing for controlling. And those controllers have so-called droop characteristic. It means if you look at the speed or frequency versus power, as frequency drops, the amount of power increases up to the maximum, of course. And that means that in order for the whole thing to work, power station must, of course, operate not at the maximum output, but they must have some headroom in order to release extra power if needed when the frequency drops. And they have to do it. In this country, no power station can be connected without the primary frequency capabilities. Interestingly, I was at the conference in Champari in January, and Pierluigi Mancarella, former Manchester, now Melbourne University, talked about Australian blackout earlier this year. And he said that actually in Australia, because they've gone crazy about liberalization, frequency control is a service, market service, where people can opt out from. And of course, power stations hate it because that means that their turbines and everything goes up and down. They prefer to work steady. So system operator has to pay people for it, and they may opt out if they don't wish to. And as the result of that, they had a blackout because the basically frequency control didn't work properly. So it's interesting. In most of the countries, obligatory service. You get not connected unless you provide it. So the primary frequency control, what will happen? So this is sudden. So this is frequency versus time. Here we are losing sizable b. So frequency starts to drop. So initial slope of decline will be determined by system inertia. So if nothing happened, that line would go down to 0. Everything would grind to the halt. But as frequency starts to drop, turbine governors start to open up, provide more power. Power will increase, so you can see the slope changes to the other, well, the second derivative changes over here, right? Here you have a point of inflection because you're getting more power. So the second stage, which is more over here, is the increased output due to the action of turbine governors. So at this point, the frequency drop is stopped. It means the generation is equal to demand. But because this is a second order system, so there'll be some oscillations, so you can see it swings back. And here it would more or less stabilize. It means that after about 20 or 30 seconds, so that point is called the frequency, oh God, forgot the word, the minimum value. It will come in a second. Nadir. So this is the nadir. That's usually 5 to 10 seconds after the drop. And after about half a minute, 20 to 30 seconds, frequency will stabilize. It means here generation is covered by the demand, sorry, demand is covered by increased generation, but as you can see, we are at the lower value of the frequency. So this is called primary frequency control. It's interesting, called primary frequency control in the whole world apart from Britain, because in Britain primary and secondary have something different meanings. They have to do with the speed of reaction, not the physics. So when we had, for example, discussion with that guy from National Grid who John organized, we were talking about primary frequency control, and he said no, this is not how it works, because he thought in terms of the terminology in this country, but doesn't matter. In the rest of the world we call it primary frequency control. It is important, it's fully autonomous, all and distributed, decentralized. Every generator acts on its own in reaction to a unique signal, which is the frequency in the whole network, in the whole system. So that's the beauty of it. I think it's 11 o'clock, so maybe we'll make a break. We'll take a break, and then after the break I'll talk about the secondary frequency control. Okay?
How long's the break for,
Oh yeah, it's a good question, which I forgot to say. I don't know, how long, 10 minutes? 1 minute, coffee, tea, check email. So let's gather, 10 past. Okay? And I should remove this thing when John came up with the right subtitle of the lecture. He said this is, should be all the questions about power systems you were afraid to ask. So by all means do ask questions, and actually you are not asking many questions. I'm worried. Maybe I'm talking about things when everyone knows about, or maybe the other way around. And there was some questions regarding three phases. This is one of the characteristic things that, especially many things which I take for granted, but people don't understand it. And I remember when Stephen Law came to Moscow to give a course. He had a fantastic course, and he published just a book about it, about similarity in mathematical modeling between internet and power systems, both on networks and etc. A very good book. I recommend it. And it is based on the lectures he gave in Moscow. So he gave that lecture, and then someone raised the hand and said, why is it three-phase? And in the middle of this very sophisticated high-level lecture, there was kind of from power engineering view, it's the first year discussion about why do we wasted 15 minutes talking about three-phase circuits. So that's why I've included it over here. So don't be afraid to ask questions. Okay, so coming back to frequency control. So at the end of the primary frequency control, once again, we are here. It means power balance has been restored, but the frequency is less than 50 Hertz. Because the controllers are what we call proportional controllers, so they'll have the steady state error. So what happens then is it's triggered the secondary frequency control, which means restoring nominal frequency. So effectively, you have to connect more generation to bring frequency up to 50 Hertz. But it's different, because now the secondary frequency control is centrally controlled. Primary is autonomous, decentralized, no one, system operators even doesn't know what's happening. Secondary frequency, these are orders coming from the system operator. It can be manual. In the GB, for example, in this country, for reasons which I could never understand, and system operator, National Grid never gave convincing answer to that question, is actually manual. Phone, used to be phone. Now maybe it will be some network, computer network, but basically they give manual commands to a particular power station by how much they should increase their generation in order to bring it up to 50 Hertz. In the rest of the world, in Europe and USA, it's automatic. The process is automatic generation control. This algorithm, which is based on the principle of integral control. Because integral control, it integrates the error, which means the difference between your nominal frequency and the frequency at the moment, and it gives you control signal in order to increase generation. And it will continue until the difference is zero. So this is integral control. So this is called, in control theory terms, it's PI type, proportional integral. So the fundamental differences between the primary and secondary frequency control. Primary is fully autonomous. All power stations have to contribute according to their droop characteristics. And usually similar types of power stations will have similar droop. For example, 5% for thermal generators. For nuclear generators in this country, it will be less, because you don't want to mess around with nuclear power stations. With hydro, it will be more. Secondary control, only some generators who choose to participate and are paid for it. It means most economic, flexible. Hydro is obvious example. Contribute directly to the secondary frequency control. And one digression digression about it. The Dinorwic and Festiniog two pump storage hydro pumps in this country, in Wales, they have been built precisely for that reason. Because what happens is, so people, for example, I've seen economic analysis of Dinorwic, which they prove that they don't understand how it could have been built, because they thought economic terms in terms of arbitrage, buying cheap energy at night, selling expensive during the day. And they came up with a number that it covers, I don't know, about only 50% of the capital cost over, I don't know, 50 years, whatever, and said, doesn't make sense. Completely misses the point. The main reason Dinnerwick was built, because it was built at the same time as the big nuclear Sizewell B was built, and they needed something which would come up instantaneously should Sizewell B drop, which is 1200 megawatts. So what happens? Some of the turbines spin on air in Dinnerwick, and they are ready to take up full load in a few seconds. So it means should Sizewell B drop, automatically Dinnerwick is being activated, all the water comes down, and in a few seconds you have full power. So that is the main reason for it. It was technical reason, it was not economic reason. Of course it also makes money through energy arbitrage, but the main reason was technical. Okay, so let's go back to this diagram. So before we were here, so here frequency stopped, we had power balance, the question is bringing it up. And so this is the period of the secondary frequency control. This is out of scale because over here is 30 seconds, up to here is about 5 to 10 minutes. Because remember, the secondary frequency control, it's manual, it takes some time, you need sometimes to start up some power stations. It takes some time. It's not that something is available immediately. The thing which acts over here quite often is given the name spinning reserve, because it means everything, the generators are spinning and they are prepared to increase power very quickly. Things which are coming up over here it takes more time. So again, National Grid uses primary and secondary frequency control terms in terms how quickly you can get power. It's not control process, it's how quickly you can get power out of them. For example, batteries are very good. Increasingly, we have market in this country at the moment also providing frequency reserve, and batteries can take part of it. Right, any questions? Yes?
So when one power plant fails, it takes only a few minutes to fully restore it.
Yeah.
But do we
I mean, frequency go back to 50 hertz, yes.
do you have an idea what would happen if two power plants failed? Like
I'll give the example in a second. This is exactly the next slide, I think. So over here is initial frequency is restored. So the difference is once again, this is fully autonomous, decentralized, this is centralized, manual or automatic. So just to summarize the number of pictorial representations of the power system. So once again, coming to the signal frequency, which is power system-wide power balance indicator. So this is basically water coming in, water coming out, and system frequency is the level. Frequency is the level of the water in this chamber. Unlike this diagram, which basically this is power system load, which is big wheel, and those little cars which are generators are pulling it up the hill. And you know that hill is not smooth. There will be some little bumps, and so those generators. So that conveys the message of the common frequency because all those cars go at the same speed, of course. And also inertia, so if they go with a certain speed, if there are little bumps on the road, we'll jump over it. So the beauty of frequency is no need for telecommunication. You can measure frequency at any point of the power system, and you can act accordingly. So that's the beauty of it. And that's the advantage of the AC system. So there's this widely available signal which controllers can act on, and the question, how would you do it in the DC system? It's not that easy. And there were questions about DC links of the break. So remember that load frequency mechanism works only in AC system. When you have a DC links, like in Europe, between different countries, it separates them. So basically, this disturbance in one part is not transferred to disturbance in another part because that, from the frequency control point of view, are separate. And there's this famous sentence. US National Academy of Engineering 2003, AC interconnector system is the largest machine ever built because of the frequency control. That was year 2003. Of course, it's no longer true because internet is bigger machine. And a few slides which are actually relevant to all the research we've been talking about here is that this is the concept of inertia. The bigger the system, the more stable it is from frequency control point of view. So it means in Europe, because continental Europe, because it's huge, so any disturbance will cause very little variation in frequency. So the frequency is very close to 50 hertz. In this country, variations, the national grid has a statutory obligation to keep frequency deviations to 0.1 hertz under normal circumstances. It can drop below, but it has to be some big event. Normally, they have to keep it plus minus 0.1 hertz. This is example of Ireland. Ireland is a little bit like Britain, yeah?
This is an average then, right?
Sorry?
This is the average frequency measured across the whole country. The frequency is the same.
This slide?
Yeah.
Well, frequency is the same everywhere.
What?
Frequency is the same everywhere. I don't understand your question, sorry.
It's the same everywhere.
Yeah. Well, that if you look at the if you look over here, all those cars go at the same speed. Now, I will talk in the afternoon. This is approximation in the time scale of seconds. If you go with sub-second scale, that those leaks are actually springs. All right, and then if you have a big disturbance, so those cars will fluctuate around the common frequency, and after a few seconds they will still go at the same speed. But I'll talk about it in the afternoon about dynamic models.
I see. So
But
you mean from the static viewpoint?
from the static viewpoint, it means we are talking about average over a few seconds. Let's say 10 seconds. That frequency here is the same as frequency in Edinburgh at the moment. If there's disturbance, there'll be some fluctuations, small fluctuations around it. So this is the example for Ireland, which is a small network with DC links to this country. And at one point, one of those DC linking Scotland with Ireland failed, and you can see big frequency deviations because the system is small, the inertia is small. So frequency dropped from 50 hertz to 48.4, which, for example, in Britain would be big event, and Europe is unthinkable. It would fall apart. While in Ireland it's normal because it's small system. The bigger the system, the higher inertia, the low frequency variations. Yes?
Iceland would be even worse.
Iceland will be even worse. They have big problems, of course, because it's a small island.
West Berlin.
Sorry? West Berlin before? Oh, well, that's a long story. In West Berlin, they used to have, before unification, they had a special schemes in order to keep this little network stable. They had, for example, big resistors, because it's a question of electromechanical stability. If they lose suddenly, if there's some short circuits, all those generators suddenly, I'll talk about it in the afternoon. But since you ask, I tell you. Now, so imagine you have suddenly a short circuit. So big generator, which is spinning, has no power to go out. So all the power which is generated goes into acceleration. So they had big resistors in order to take power out of the generator to stop it losing stability. Of course, after unification, they connected everything together in the German system, no problem. But this is legacy.
Another stupid question. Why you never have a fluctuation above 50? Why it's always below?
No, I'll show you when there are bubbles as well.
There isn't.
Yeah, of course, they go up and down because you have never. Well, basically, this event usually consists of dropping something, right? So again, Ireland, as you know, has problem that they have a lot of wind. I think the highest penetration of wind generation in the world as far as this isolated system is concerned. Denmark has more, but they're connected to the rest of Europe, so they can borrow. Basically, they from inertia point of view, they're just part of the same system. Ireland is separate, so they've done a study a few years back, and this is wind and import. Import is also asynchronous generation, so it doesn't react to frequency. This is demand, and they reckon that about 50% is safe operation. So they used to have that at night, especially when the wind was strong and demand was low, wind generation would be more than 50% of demand, and they had to spill it because it was dangerous. At the moment, I think they have additional measure. They bring it up to 60 or 70%, but they cannot bring it more because then inertia would be low, and if you have an event, you drop something, then the nadir would be low, very, very low, and it can even lead to frequency collapse, basically blackout.
Can I ask why you don't have an AC connection between Ireland and
That'll be next slide.
always the next one?
Always next slide. Well, that's a typical question, so that's why I know. I'll come back to it in a second. Well, of course, these are, well, the problem with low inertia, there's a technical thing, so there are technical fixes. So for example, there's synthetic inertia. A lot of wind is connected. You can use the one way to increase this penetration. The wind generators can be forced to participate in frequency control. Initially, they didn't participate. Now they're forced by the regulation in Ireland to participate in frequency control. So this is one of the way. The so-called synthetic inertia, like those wind generators are connected by means of power electronics. And when you have a power electronics, you can simulate that it behaves like AC. So it means if frequency drops, it takes more power. Wind, at the end of the day, wind turbine is a turbine. It has some inertia, so you can draw temporarily more kinetic energy from it by control means. It means it will slow down. It may behave like a traditional generator. So this is referred to as synthetic inertia. And people talk about the market for inertial response, basically pay people. Because if you decommission traditional power station, you may leave all those generators running, just spinning, in order to provide inertia. So there are many ways of dealing with it. It's not a showstopper, it's a technical problem. And a few nice slides, and again, my first version of that presentation was over 10 years back, so I'm afraid some of the slides are a bit old. So for example, this is typical events, so this is so-called TV pickups. This is April 2011 royal wedding. There have been some newer royal weddings, but I don't have slides. So this is when William got married. So here you have power demand, and here you have a frequency. So what happens is people watch TV, right? And if something interesting happens, is they stop doing whatever they are doing and they watch TV. That means then demand drops dramatically. So that's why. So here you have what happens. So William and Harry leave Clarence House, and etc. So people watch them. The bride arrives, which is everyone wanted to watch. How she was dressed like. So that you can see demand. So that normal demand would go like that. You can see huge gap because basically people stop doing whatever they were doing in order to watch them. And the frequency goes over the place. It does not follow the path of generation demand because system operators, of course, know about it, and they have TV in their room. They have TV not in order to watch TV, but basically check what's happening. So when there are interesting TV programs, they know the demand will drop and they have to respond to it. So that's why you see frequency behaved quite reasonably. So this is 50 Hertz, this is 49.8. As I said, the statutory regulation is to have 0.1 Hertz, which is up to here. So that was they got slightly below it because it was big events. You asked about 50 Hertz. See, here is above 50 Hertz. So regularly, it goes up and down regularly. So I have more slides like that. Again, this is show you how ancient those slides are. This is England versus Argentina 20 years ago. I should get some newer slides, but I didn't have time to do it. This is when Beckham was showed the red card. Semi-final, England lost on penalties as usual at that time. So what happens with football? And this is old story about it. So as you can see, so this is normal demand shape, and this is what happened during the match. So you can see huge drop over here of the demand. So what 2,200 megawatt drop of demand when people are watching the game, and then suddenly increase in power here at the halftime. 2,100 megawatt, which is two large power stations. And there are different theories why there is this huge increase in demand at halftime. And one explanation is that the British customs, people in the continent, when there's halftime, what do? To relax? They open a can of beer. In this country, what people do? They go to the kitchen and switch the kettle on. So demand shoots up. The other theory is that people go to a toilet, and if they go there, they flush water, and they flush water, all the motors start to work too, just to increase. Different theories. Never mind. See the huge demands over here, increases in demand drop, and then increase, drop, and increase again. So National Grid has to model that. And then there's a question that it can go the other direction as well. For example, this is the total solar eclipse. So that's literally everyone. That was again nearly 20 years ago. what happened was that the last total eclipse, and the next one will be, I don't know, 50 years time or so. So everyone was outside, you know, watching the sun. So you can see drop, 2,200 megawatt drop. We were watching solar eclipse, and again, National Grid will have to manage it. And that happens every day. This is Britain Got Talent, 8 years ago, kind of normal program. As you can see, also, you know, just picks up and down, so those so-called TV pickups. So that's why system operators have control rooms, TV screens. Interesting things. This is, you've heard about this Earth Hour, have you? So this is the Earth Hour is the action by, I don't know, National Wild something, I can't remember the organization. So they showed, so in order to save the Earth, we should all switch off electricity during this Earth Hour, which is whatever time, a certain time of the day. And of course, it's total idiocy. Good intentions, people don't understand it, they haven't attended my lectures. I would have told them they're idiots. Because imagine what would happen in terms of what I've told you, what would happen if really, indeed, everyone switched off electricity exactly the same time. And then switch it on at exactly the same time, everyone in the country. There's no way National Grid or any other system operator would control it, because there will be huge sudden increases and decreases of demand equivalent to either 10, 20 power stations. It's impossible to manage it. Let's look what happened. That was 2011. Again, I didn't have newer. So this is the normal shape of demand at that time of the day, which was that between 8:30 and 9:30. And you can see what's happened. So this is the norm. This is part of the sloping, because this is in the afternoon, so demand was sloping anyway. So this is what happened. So if people did follow, you would see a sudden drop over here, and here sudden increase. Luckily, nothing happened, so people didn't listen to those idiots. So maybe they didn't show the appreciation for the demands, for this idea of that we should save environment, but in a stupid way, and nothing happened. But if I repeat, if it did happen, if people switch off demand, there will be a huge problem for the system operator. Now is the question over there. Okay, is it what happens when there is more than one event happens? So this is again what happens when there is not enough spinning reserve to cover an unexpectedly high loss of generation. So that goes to this n-1 reliability criteria. As I said, the largest event in this country is loss of sizable B, and this is what happens when we lose sizable B and something else, which is something the system has not been planned for. So the normal reserves is 1320 megawatt reactor at sizable B. We could keep more on reserve, n-2, but that will be very expensive, so that's why it's n-1. But unlikely event does not mean impossible, so the question which was asked is what would happen if something like that happens? And this is actually, as I said, I'll come back to it, and this is what happened. This is, I can't remember which year it was, 2000, I think 8 or something like that. So what happened? This is the frequency trace in the UK. So here we've lost a Scottish generator, which I think is now has been decommissioned because it was, they call it in the report generator A, but everyone, it was Longanet, I think. So we've lost Longanet, which is 345 megawatt, which is nothing special. But then within 1 minute, generator B, which was sizable B, as you see, 1237 megawatt, basically almost at the same time. So as you can see, so frequency dropped, but then it was stopped by the so the two plants dropped, so the total drop was 1582, which is more than 1320, which is planned. So actually it wouldn't be that bad, but because there was a huge drop of frequency following the huge loss, the frequency dropped to 49 points, below 49, just about 49 hertz. We started to lose wind power plants. Now wind power plants have, or used to have at that time, other frequency relays, which would disconnect them if frequency is too low, basically to get them off the system, because it's something wrong going on. So when there was no much wind, it was just to get rid of them, because they could cause problem. Now they cannot do it this way because there's too much wind, but that time there's normal. So here we started to lose wind. So you see frequency was dropping down to 48.8 Hertz, which is very, very bad. So what happened then? So when the frequency was dropping, National Grid reduced voltage because they could see what's happening. You see time scale over here is about 2 minutes, so they could do something about it. So they started to reduce artificially voltage in the whole system. A lot of power is heating, which is resistive. So you reduce the voltage, V squared over R power demand, so you reduce the demand. So they reduced demand by 1200 megawatt, but frequency was still dropping, and you see 48.8 dropped to 48.8 and then started to increase. This is because all the power systems have so-called under-frequency automatic load shedding. And they have a number of stages. So when frequency drops in this country to 48.8, a number of loads basically will trip automatically because you need to protect the system. The only way you protect the system is to reduce the demand. There are usually 3 stages. So it'll be 48.8, then I can't remember, 48 something, and etc. The main thing is to protect the system demand, so you have to trip some demand. No one knows which loads, because it's of course politically sensitive issue, because why should you black out me or not someone else? You can be sure that London is not automatically shed. It's probably some poor guys in Scotland or Wales or God knows where. Anyway, so automatic load shedding started and the frequency was recovered. But it was apparently pretty close shave. It was one of the most dangerous instances of operation in the history of National Grid. The system is pretty safe. So they had a lucky escape. But the lesson from that is the frequency, the control of wind power has to be modified from the point of view of frequency, because that was the reason that they dropped. Yeah.
So, you know, the lucky escape or whatever, are we talking something other than significant blackouts?
Well, lucky escape in the
Damage to equipment?
no, just blackouts. Well, 2 slides down the line or 3, I'll show you an example that is actually not only that. But basically, so as I said, those under frequency load shedding means that you trip more. If the frequency, if there's something else happened, the frequency would drop more, basically more load would be disconnected after reaching the next stage of the under frequency load shedding.
It's kind of controlled blackouts because
There's a control blackout.
you're choosing to disconnect customers.
Well, the term blackout is used wide area blackout, like the whole country goes black, right? So this is you disconnect on purpose certain customers.
Right, so it's not really a blackout.
Well, for them it is, but from the system point of view, it's not a blackout.
I was actually having an email exchange about this yesterday. It's one of these words where it's used in a sufficient number of different contexts that it's one of these things where if someone else uses the term blackout, you have to ask them what they meant, and if you use it, you need to explain.
No.
Because as an ordinary customer, I'm not really going to notice either the reduction in voltage or the reduction in frequency. I mean, I'm going to use less power, but I'm not really going to notice it. My computer's still going to work, my TV's still going to work.
It may get colder slightly, because what happens, you know, all those resistive heaters, you know, voltage drops, it means they'll get colder, but they have thermostats. So those reduction of voltage will help in the short term, because of course thermostat will increase the settings, so it will recover, but that gives you breathing space. But just a minute, because I forget otherwise. So there's important question of definition of blackout. So I was mentioning Russians, which they have this emergency controls, and there was a paper about a few years back in IEEE Transactions written by Russian. There are a lot of now Russian control engineers working in the States, and they're talking about this emergency controls in Russia. And as I said, because the system is spread, they don't run it to n-1, so they have to have those emergency controls. And they claim, you know, this huge success, because in Russia there's never been a big blackout, despite the system being extremely stressed. Big success. But what do they mean? It means, what does it mean emergency control? It means if something happens, they trip people. They would trip the whole towns or even regions in order to save the whole system. They don't call it blackout because it's not uncontrolled. They control it. But from the point of view of big, poor guys, you know, in the town in Siberia, God knows where, you know, they've lost power. So for them it's a blackout. So as Chris said, it's a question of definition.
Yes, please. Just a question. What are the theories, or what are the possible theories to explain the unexplained frequency deviation? Or are there any theories?
What do you mean?
Here, in the graph. So
Over here?
yes, please.
Yeah, so that's why I'm saying those the wind powers. So the wind turbines, when there was just very few of them, they have under frequency protection, and they have what is called rate of change of frequency, which is derivative of frequency, because there was a protection. Those wind turbines are somewhere down distribution networks, and if the distribution networks, well, the typical reason for a blackout is not something like that, but the digger cuts out a cable. You know, digger digs up earth and cuts through a distribution cable, right? And the villages, whatever, they lose suddenly power. This is 90% of power loss. It's those kind of things. Now, if you had wind turbine connected to that part of distribution network, the wind turbine would still operate. Of course, it will still produce electricity, but you need people to go out and check it, and they cannot have active energy source acting over there because they would be electrocuted. So those wind turbines will have this rate of change of frequency, ROC-off protection, which senses when the frequency suddenly changes. And if frequency suddenly changes, something like that, it means there is a danger that that part of the network was islanded, and if it is islanded, they need to switch off generation. They need to switch off those wind turbines, right? And that's what happened over here, because look, huge drop of frequency. So from the point of view of those wind turbines, they said, we are islanded, we need to switch off. And that was the reason for those wind power, those changes. I'll come back to it again with another example of Europe. Okay? So that blackout nearly happened due to loss of generation, but as I said, there are those a number of famous blackouts which happened during the transmission faults, lines falling. So what's the typical scenario leading to this cascading blackout? And that's why we have this N-1 reliability. So when a line, so blackouts usually happen when you have N-2 events, because as I said, everything is designed to N-1. If something happens, N-2. And
urban networks are planned to N-2, not operated.
Planned, yes, sorry. Well, I'm saying we're urban networks usually, because a lot of people in London, for example, that N-1 standard, because you know it's London, a lot of people living.
Could you explain quickly what exactly this N-2?
Right. So, how blackouts, those cascading blackouts start? So you have line trips. Due to the principles I said, the power flow in the network depends on what's going on everywhere else. So if a line trips, it means that power flow is distributed to other lines instantaneously. If it's distributed instantaneously to other lines, the other lines may get disconnected, may be overloaded, and then disconnect. So that's why, as I said, the power systems are operated to N-1, so it is safe not only as it is now, but if you assume any single line fails, power gets redistributed, it's still below the limit. We are safe. So that's why I said blackouts happen due to N-2. Something else must have happened, but this N-2 can be not only just in electrical terms, but it can be something else, like people do something wrong, and I'll give you examples of that. Okay? So this is the famous blackout in 2003, where northeast of United States and Canada went black. So this is Statue of Liberty in New York. As you can see, everything in the background is black. But of course, Statue of Liberty had its own power supply, so it was lighted. So how it happened? It happened over here in the area of First Energy near Cleveland, and then it spread the whole network. So basically, the trees were not planted. So the line, how blackouts happen? When the line is overloaded, too much current flowing, so it's heated, and it's heated, it extends its length, of course. And when it extends its length, it touched one of those trees. So that's why you have to make sure that no trees are below a certain length, a certain height. Here they were not maintained properly. It means one of those conductors touched the line and it tripped, which is normal thing. So normally the system operators would have spotted it and you would have take some operation. However, the local operator, which is Midwest ISO, state estimator to the whole area, state estimation which assesses the state of the whole network, was down for whatever reasons. An alarm and logging system in the local utility, First Energy, failed 1 hour before the cascade happened. And not only it failed, but the control room didn't know that it failed. So they were blind, but they did not know they were blind. So, and this is what I mean by general N-2, which is the computer failure. So line tripped, but from the control room didn't know about it, so didn't take any action. And also there was no collaboration between system operators in the area. I showed you the map with the different colors. Each area, United States, is a mess. It's a mixture of different operators operating for historic reasons different part of the networks, far worse than in Europe. At least you have countries. So so those 3 lines tripped one after another, and the system operator didn't know about it. Control room did not know about it. And you can see the effects that this is regarding to your question. What happens when the line trip? So here, the first is like 5, whatever it was, one of the line trip. As you can see, this is the loading on each of the lines. So when the one line tripped, the loading on the other lines increased because the power had to be carried by some other lines. Here, the next one line tripped, again power loading increased, and then the next one tripped, and again power loading tripped, and you had this cascading effect when one after next tripped. Not only power loads get distributed, but voltage drops down because the lines are heavily loaded. Ohm's law, voltage is current times impedance. Current increases, it means voltage drop increases. So you can see each of the trip was accompanied by dropping voltage on the other substation. Dropping voltage is very dangerous. I'll talk about it later on. It's to do with voltage stability. Until we had the total blackout. So this is what happened. So that was the initial power flow. So power would flow. This is where it all started. It will go around. Here is Canada, around the lake Erie, or whatever you pronounce it, to supply the northern part of Canada. So when that line tripped over here, power had to go somewhere, so it went through the other areas. So it means those areas were overloaded. But that's because those areas were overloaded, so power had to flow over here around it. So this is the line of the blackout. More, so you can see, and here it's starting to hit New York. New York is, I don't know, several hundred kilometers or maybe more from the initial area, and suddenly it got hit by huge flows. They didn't know where they're coming from. And again equipment, I think here is New York, yeah. Again equipment tripped. And finally, this is the whole area of the blackout. So event over here spread across the whole area because of this cascading effect. Here you have the speed of cascading. So look, initially things go, so this is how the whole thing started. So there was the single line trips. This is the number of lines failing and number of generator units failing. So the line started to fail initially very slowly, but then from this point is basically like an avalanche. No way of stopping it. So this is lines failing, and this is the generators failing. Because as frequency drops, voltages go down, then power stations start to fail as well because of the equipment. So that gives you an example how important it is to have automatics in place, because once you got over here, no way of stopping it. So you have to prevent it happening. Some another examples of the blackouts, interesting. Another one, it was in Europe, 2006. So what happened? It's actually the Germans, would you believe it, messed it up. What happened? There was a ship passing through a river, which was planned thing, right? And because that ship was passing through a river, they had to de-energize a line because it was too close to the top of the ship. De-energize it means switch off the line. I mean, the line was there, but there was no current going through it, right? so there was no danger of electrocution. And then just 1 hour before the event, a couple of hours before the event, they've changed the timing. I mean, there's nothing special about it. They do those kind of things all the time. But what happened at that day, for whatever reason, they brought forward this hour, and the local utility, E.ON, should have done the whole calculations to make sure that if they switch off that line, nothing happened. They haven't done that. They trusted their judgment. They said, everything will be fine. Well, it wasn't, because then you had this cascading event, because actually when they did trip that line, they switch off that line, the other lines got overloaded. Then they did something which is called the bus splitting. Patrick, you remember Patrick Panciatici? He's talking about it. So what happens normally, bus is, if you look at the power system schedule, you'll have, so this is a bus bar, which is point of connection, and you'll have a number of lines coming from it, different transmission lines. But actually that line point of connection, there is some structure inside it. You can separate it, for example, in such a way that you remove the connection between them. This is called bus splitting. It means the topology of the network changes completely. So they've done this bus splitting, hoping, because again, based on their judgment, they thought the power flows, because you change topology, and if you change topology, power flows change, and they thought they would go down. They actually went up. And what happened is that there was a cascading blackout, and the customer as far as Spain and Italy were disconnected. It was spread over the whole Europe. Again, definition, whether it's blackout or not, system operators, they don't call it blackout, they call it system separation. Because what happened, it wasn't blackout across Europe. Certain customers was disconnected due to local protection, but the whole continental Europe, which normally operates in one area at one frequency, got separated into 3 parts. So the dominant power flows were from the northern Germany, because there was a lot of wind at the time, going here to the western Germany. The system separated across those lines. Again, people ask me, why did it separate across those or then? I have no clue, and no one has clue. Due to some characteristic, basically, the nature kind of organized itself in such a way that that was the line of separation. Basically, those lines were disconnected.
Like I was not in the Netherlands at that time, but apparently there was only one village close to the German border had problems.
Yeah, that's right.
9 months later, lots of babies. But,
well, there's another story. Well, actually, regarding the babies, there was a famous story. There was blackout I was talking about. The blackout, New York had 3 big blackouts. The first one, I think, 67, then was 77, and then there was this one, 2003. And there was the standard joke that a lot of babies born 9 months later, because if there's no TV, there's no internet then, what people could do. But apparently, it's a fake news. That's what I've heard. Never mind. No, but that's true. That actually, so people were disconnected due to local protection acting in different areas, but Europe as the whole was generally fine. But it did separate into areas. So that means because there was a power flow going from the east to the west. So when you come through those lines, that area had surplus, so power frequency went up to 51.4. Here there was a huge deficit because that lost all the supplies. 8.9 gigawatt deficit, so the frequency dropped to 49 hertz. Southeast area, there were just little deficits of frequency, there was no problems. But over here, there were huge problems. There was again very, very close shave, the near failure of the whole system. So here you have a frequency. So of course, so after separation, as you can see, this is the west, and this is the Balkans. Sorry, this is the east, this is the Balkans, this is the west, frequency drop. They're operating different frequencies, so they tried to reconnect them. So you can see those things over here. They were trying to reconnect them, but they were far apart, so it failed here, it failed here, and then finally they managed to connect them after half an hour or so. You remember when I was talking about phasor measurement units? Some of you were there when I was talking about this. So that graph was not possible for this American blackout, because those phasor measurement units, which measure frequency and which are GPS synchronized in different parts of the system, were not there. But in Europe, we're already there, so you can see traces, coordinated traces of frequency, instantaneous frequency in different parts of the system. So there was there's eight attempts to synchronize the system before they managed to synchronize it. And the last blackout I wanted to talk about is Italy. And again, and then coming to the load shedding question. It's interesting. So what happens? So this is Italy, here was Switzerland. So here one of the lines failed again to the same reason. You know, Switzerland, Alps, border, tree was too high, line touched it. And the line tripped. And here the problem was that this is the general problem in Europe, that each country operates on its own. And there was still dispute going on whether so the dispatches are not coordinated, and apparently the Swiss did not tell the Italians at the time what happened, which of course the Swiss dispute that claim. So there was going on discussion. Anyway, the Italians did not know that the line failed on the Swiss side, and they thought they were safe, but they were not safe. So when that line got tripped, it means it overloaded the second line, it tripped, and then all the lines connecting Italy with Europe, with the rest of the Europe, tripped one after another, typical cascading blackout. So basically Italy became an isolated island electrically from the rest of Europe. Italy is importer of power. As I said, they voted twice against nuclear and didn't build enough power stations, so they import a lot of power, mostly from France and Germany. So here what you have, so this is frequency and this is power deficit. Here you have scale frequency, here is a power deficit. So if it goes down, it means huge power deficit. So when those lines tripped and Italy was separated from the rest of the continent, you can see huge deficit. So what happened? It was all sensed. Of course, the frequency drop was sensed. So first they disconnected pump storage. Italy, a lot of mountains, so they have a lot of pump storage. So that happened during the night. So during the night you pump water up and you let it go during the day. So when the frequency, of course, the first thing they stopped those pump storage plants which were working all the time. So as you can see, so the first deficit decreased, but because it dropped to, where is it, hertz? Over here, to about 49 hertz. So here, at that point, started load shedding. Frequency was very low. This is similar to what I was telling you about Britain. Frequency was low. It means automatically load got disconnected during the night in Italy. So it worked. It means at this point, you can see the deficit, power deficit is zero if you then went positive. So situation was apparently safe. But the problem was there was a huge swings of frequency and the voltage dropped. So you started to lose power stations. Because power stations are quite complicated equipment. They have a lot of pumps, which pump water, which pump everything. And if there was a problem with frequency and problem with, especially with voltage, those pumps stop to work, and the pumps stop to work, power station disconnect. So over here, you started to lose more of the power stations. You can see again there was a deficit of power, and because there was a deficit of power, the frequency stopped dropping. Continued dropping. Finally, it dropped. It came to 47.5 hertz, more or less, which is the last stage of the automatic load shedding. So they tripped everything there was to trip in Italy, but it was not enough because power stations were tripping at the same time. And you had a total blackout. I mean, absolute total blackout, but that was sound like 3 o'clock at night, so many people didn't even notice. They got it up and running in the morning. Interestingly, again, a little digression, despite 12 o'clock now, you have so-called cold start. Every power system has to have plan for cold start. Black start, sorry. It means when something like that happens. Britain, every country has it. And I read a paper, Italian system operators, they published a few months earlier, how they check that all those black start works. The problem with black start is that it never happens. That means you're never sure whether it will work or not. They did actually check it, and it worked. So they get this, many people didn't notice it because by the morning everything was fine. But anyway, it was huge blackout. And the few last slides touching about DC, because again there were questions about DC. If you look, so this is the links, submarine links between countries in Europe. Britain has 2 over here, Netherlands and France, and there are more being built, and this is across Baltic and North Sea and etc. Here are links between Scotland and between Ireland and Britain. And for the reason which I will explain this afternoon, those links are DC, not AC. That means that if you have any problems in Scandinavia, those problems are not exported across. So when you had problems in Europe, in Britain nothing happened. The same in Scandinavia, nothing happened. Because DC links give you, they have some control, power electronics control, they'll give you exactly the amount of power it is scheduled to give, no matter what. That means that the frequency control will not act across those DC connections. Unless you are in Australia, when there was this blackout, when actually there was some frequency control schemes which work across DC connections, and that caused problems. So the second reason for those DC links, as I said, is a technical reason that when you have a submarine cable, it has to be DC rather than AC. But the second thing is they provide this electric separation between systems, so the disturbance doesn't spread. And as I said, this disturbance, European disturbance, did not affect surrounding areas. And I think this is the last slide, so I managed to finish just on time. If you look at the US transmission network, it is separated into 3 parts. Western interconnection, Eastern interconnection, and Texas. And there are DC links between them. And those DC links are not because of submarine cables, because of course this is land connection. Those DC links are literally size of this room, full of power electronics, separating electrically those different systems. The main reason is this AC mechanism. They reckoned, and that was separated very, very long time ago, they reckoned they could operate the whole US system as one, but they reckoned they couldn't work because it's too big, too difficult to control. So it is on purpose separated in 3 interconnections. So if something happens in West or in East, does not export across the border, and here as well.
Imagine that you do East and West, but why is Texas different?
Sorry?
Like, why is Texas then separate?
At this point, all the Americans start to laugh because there's this reputation about Texas, everything is different. They consider themselves as the kind of completely separate people that are different.
I think one reason why they don't want to consider joining is that because the remit of the Federal Electricity Regulatory Commission flows from the Interstate Commerce Clause in the US Constitution, which gives the federal government the power to regulate interstate commerce.
No.
So if they join one of the AC interconnections, then the federal regulator would have full influence over them.
Yeah, this is this regular debate. In Europe it's simpler because there are countries, and each country controls its own network. In United States, remember, United States are a federal country where states are very strong. So states control what happens within their own network, below a certain level, but this transmission overlay, which is shown over here, the highest level, is under control of FERC, Federal Electricity Regulation Commission, or something like that. And there's always dispute about, if they want to change the market or whatever, there's always dispute that they're being challenged by the state regulators, because there's a phase in every area between Federal Regulatory Commission and the local state. They fight for power and the control. But that division is purely technical, as I said, because they reckon it's too difficult to control the whole system as well.
Can I ask about that? If all the small systems like Ireland are inherently unstable because they're small,
I wouldn't say that in unstable,
they're more unstable.
kind of more volatile.
More volatile, okay, whatever. And then big systems are uncontrollable. Is there a happy medium? And is there a theory that tells you what the happy medium is?
There is no theory, but there is a gut feeling. So here you have this happy medium. They decided the whole states would be too much if we cut them in half, and well, let's leave Texas at the side, it'd be just about right. About 10 years ago or 15 years ago, I think it was in the late 90s, so those after Berlin Wall went down, and Russia was considered not was considered a friend again. There was the ENSO, or UCT as it is, and it's the Organization of European System Operators. They commissioned a study because Russia wanted to join, connect their system to the rest of Europe in order so they could export power, of course. There was a big study which came to an obvious conclusion. No way. Nothing to do with politics. But the Russian system is big. It's huge. It stretches, I think I'll show you tomorrow as well. There's one slide about it. No, it isn't, but never mind. It stretches basically from the border of Poland and Baltic republics to Siberia. It's inherently stretched, difficult to control. So if you connect them together with Europe, the whole thing will just break down. It's just too much.
And yet, from a naive layperson point of view, you might think that time zones were an advantage in smoothing out the system.
That's right. So that's why you have those DC links. So that's why they did over here DC links. They can take advantage. Remember, the time, again, there's, I don't know, about 6 hours, I think, difference between east and western coast of the United States. So you have different patterns. And that transfer across, but DC. The same with Europe. So the conclusion was we can connect but only by DC, but not AC, because that will be too difficult to control. If you connect by DC, you can take advantage of the differences in the time zones, because you can transfer power across, but it's fully controllable. You don't have those effects of frequency. Because then they came to conclusion, again, sorry. So when the wall went down, they connected Poland, the former communist republics of Eastern Europe, like Poland, Hungary, Czechoslovakia, and etc. They got connected, of course, to the Western Europe, and the line of separation was between Russia and those countries, and there was a big exercise in order to make sure that all the controllers act accordingly when you connect Eastern Europe to the Western Europe. And there were instances they did not get everything completely right, and there were oscillations because the controllers started to fight each other. Those turbine governors, a friend of mine was actually involved in that studies, and they decided, well, they discovered that some of the controllers was wrongly set, and basically Polish power stations started to oscillate against the French ones because there was some mismatch of the control settings. So this is a typical danger of big power systems. So imagine if you do the same thing with Russia against the whole Europe. It's a nightmare. So they decided no way. Yeah?
DC links help to with the problem of loop flows also?
Yeah. Yeah, so I had that slide. So basically, so that's why I said one of the earlier slides. So a lot of those phase shifting transformers control loop flows both on the western and eastern side of Germany. So a lot of in Belgium and also Poland and Czech Republic. So they try to push those loop flows inside Germany. And I'll tell you the theory behind the phase shifting transformers after lunch. Another questions? Okay, thank you very much. So see you at 2 o'clock after lunch.